information on subduction zones and continental crust and what's happening down here on Earth. Thanks very much.
Thank you. So the title is Creation and Destruction of Continental Crust at Subduction Zones. Subduction zones are environments that I have studied quite a bit for the last 8 or 10 decades, or however long I've been at this. And actually most of the equation in terms of creation and destruction of continental crust does occur at subduction zones, but it's not 100%, and I'll talk about the other bits that might contribute. Generally, the kind of research I do tends to be focused on a given location, and I try to understand that. But I thought I'd give this sort of general global view talk here, since you're really planetary people, and sometimes it's good to have that real broad perspective rather than just focusing on a particular thing. So this is showing the distribution of continents and oceans on this Mercator projection. About 30% of the planet is continents, and the question is, at what rate do the continents grow or decrease? And do they change their volumes over time? And it sounds like a simple question, but in fact, it's a very difficult question, and I don't really have an answer for you. I can give you kind of some latest thinking, but I'd rather instead talk about what are the elements of the different equations. So here's a diagrammatic sketch of a subduction zone, and actually there's no subduction zone that has all of these elements well displayed, but you find these elements in various of them. You have subduction, where the oceanic lithosphere goes down deeper in the earth into the mantle, where there's a partial melt, and the rocks actually can flow very easily. The lithosphere does not have this partial melt, and it has a much higher viscosity. So the downgoing lithosphere brings with it a fair amount of water in sediments in the ocean crust and in the upper mantle, and as it goes down, that water is driven off. The minerals dehydrate, and that results in a flux melting of the upper part of the mantle, the asthenospheric mantle, that produces a partial melt, and that generates volcanism and magmatism within the crust. So if this isn't showing the crustal thickness, but this is diagrammatically showing a thickened mass that is thickened because mostly magmatically. Just one slide indicating the history of continental growth, and I can't vouch for how robust this is. Basically, it's based on numbers of uranium lead dates that have been taken through time from continental areas, measured in zircons. And you just plot the number of ages, and you find that there are these peak times. One just before 3 billion, or just after, about 2.8 or 9 billion years ago. One peak about 1.8 billion, one about 1.2 billion. And if you look at various people's curves for the generation of continental crust through time, they look something like this sort of S-shape growth curve of crust through time. Now, if you triple the number of dates, would it look identical to that? I don't know. I don't study these older rocks. But, the modern thinking is talking about growth something like this. So we're down kind of in this area and not in the real massive times of continental growth. In the earlier history of the Earth, much of the continents were formed. So there's two parts of the equation, the growth part and the destruction part. So I'll start with the growth part. Continental crust can grow by volcanism or magmatism at subduction zones, island arcs that form in subduction zones. It can also form by volcanism at or magmatism at hot spots, and these can occur anywhere on the Earth, and also by accretion of oceanic material to the continents. So as a result of subduction, material is scraped off, it can be added to the continents, and that can go into growth. So I'll first talk about the growth part. Here's a cartoon of a subduction zone. People call this the Subduction Factory. Materials brought in on the ocean plate to the edge of the continent or to a subduction zone. That material goes down into the mantle. It's processed. Some material goes out as volcanics. Others are the residual are taken farther down into the Earth. And in some subduction zones, there's good evidence that these can go deep down into the mantle, can cycle through. New material can come up in these plumes or hot spots, and you sort of have this cycle. Well, there's more to the cycle, especially in the subduction zone. Now the question is, how do we quantify how much magmatic addition is happening to an island arc in a subduction zone? And this was one of the first really detailed studies, even though it's highly exaggerated vertically in scale. Here's the subduction zone, and this is the Izu arc south of Japan. And these different colors reflect P-wave velocities. And velocities of something like 6 to 6.5 kilometers a second are consistent with a kind of granitic material, the kind of material that forms continental crust. Then you have the higher velocity, lower crust that is more residuum of that melting, and then the upper bits of volcanics and some sediments. So it's this kind of study that gives an idea of how much crust is generated, and knowing the ages of the volcanics and when the arcs formed, one can get an idea of the rate of growth of the arc. Here's another cartoon, again showing the slab going down, drags down isotherms, so that's a very cold slab going down into the Earth, dehydrates, generates magma, that comes up to the surface to give you crust that could turn into continental crust. Another example of a detailed study is the Aleutians. Here's the downgoing crust, and lithosphere is thicker than that. The whole slab would be something like this. And you notice here's a layer that is of those intermediate velocities that could be equivalent to, crustal velocities. But in the Aleutians, that's about the same thickness as the oceanic crust. So it's not clear how much new granitic material is being added in the Aleutians. But you do have some idea of the total volume of the arc and how long it's been active. Now, another source of magmatic material is these hot spots, or what are called large igneous provinces. And those are scattered throughout the Earth, largely in the oceans, but not entirely. I mean, you can see in Africa, South America, there should be some up in Asia, etc. But scattered throughout the Earth are these large igneous provinces that range in age from Mesozoic to recent. So Hawaii is out here. Notice this big blob over here called the Ontong Java Plateau, just off of New Guinea. I'll focus on that as an example. Again, here's a closer view of the Pacific. Here's the Ontong Java Plateau, and it's colliding with these island arcs that are off of Australia. If we look, even closer, you see that this is a fairly large area. Let's see, that's 5 degrees, so it's about 500 kilometers, or this is over 1,000 kilometers. So this is a pretty big feature, and its thickness is almost that of a continent. But you don't think of the Ontong Java Plateau as a continent because it's not above water. I think continents above water, this isn't above water, but it's about as thick as a continent. And it's also not made of real continental material. It's largely basaltic in composition. But it's causing a lot of damage here. Bits of it are being scraped off. Here's a section across the Solomon Arc. So here's the subduction from the south. There's the Solomon Arc, and here is this big block of Ontong Java Plateau. And a piece of that has been accreted and shows up in some local islands of the Solomons. So the question is, how much of these plateaus actually get accreted to the continents? Possibly not very much, maybe a little more than not very much. And that brings us to the question of accretion. Here's another cartoon of a subduction zone. Here's the volcanic arc back here, the downgoing plate. And this is showing sediment or sedimentary material being scraped off and forming a large wedge in front of the arc. And so that's a process that can accrete new material to the front of a continent. Now the question is, what is this material? And in fact, where you have large accretionary zones, much of the stuff that's accreted has been eroded off the continents, deposited in this trench out in front, and gets plastered back to the continents. So that the amount of new stuff is probably fairly small in terms of accretion. Here's kind of a cartoon of the process of accretion. It's sort of similar to a snow plow piling up a pile of snow out in front. That is what many of these accretionary wedges look like. This is a well-constrained section across the front of Taiwan. This is about 8 kilometers from sea level. And that is showing, here's a layer coming in off of China, this thick section of sediment coming off of China. And you notice the stipple layer that gets imbricated on itself over and over again to build up this big mountain range of Taiwan. And that is the process of how mountains get built. And you can see the same kind of thing developing in an outcrop. I mean, here's a hammer about 1 foot long, and you can see these big imbricates that that represent the accretion and shortening that's going on within this zone. Here's a series of sections across 3 mountain belts. Here's another crossing through Taiwan, the southern Appalachians, the Canadian Rockies. You can see all of them have the same kind of pattern. They differ in detail, but they all show this imbrication of material stacked up to build a mountain. And if that material is coming from something other than old continental debris, then you've actually added stuff to the continent. Otherwise, you're just recycling it. In the oceans, here's an example off southern Japan called the Nanchi Trough. And here's a profile through here that shows, again, a large amount of accretion. This is 10 kilometers for scale. Large amount of accretion, very young accretion, and sediment being brought down under it, and then older accretionary stuff. So there's a huge pile that's developing, again, out in front of Japan, but much of that eroded off Japan. And one other example off of Barbados. Here's a layer of sediment coming down. This upper bit is being scraped off, and you see this thicker and thicker pile of sediment that you can't see any detail in because it's so highly deformed. And this is looking over the length of the whole pile. You can see the downgoing stuff. And then this is just thickening and thickening to a greater amount until you get to Barbados, which is equivalent to this position. Stands above sea level with about 20 kilometers of imbricated stuff underneath it. Now, that's not all coming off the Lesser Antilles, but much of that is coming off of South America. And so, again, it is recycled. I mean, Barbados is up here, and you have these big rivers, of course, coming off South America. They flow north, fill in that trench. The stuff gets plastered back in. Collisions, these build very large mountain belts. India colliding with Asia, Arabia with Asia, giving the Zagros, the Alps over here. And still the question is, what's the balance in this? You have two continents colliding, you get a big mountain, but are you actually adding or subtracting more stuff? And you can be doing both, actually. In the early stage of this collision, there were a lot of things that were added from the oceans, and you can see that process now here off of New Guinea, a very similar process that not necessarily was exactly like this, but more like the Western North America. So you have Australia and this whole series of island arcs over here, Indonesia and Papua New Guinea, and Australia is colliding into them. Ontong Java plateaus colliding the other way. And that's squashing a lot of stuff that was created in the oceans and island arcs, squashing it onto the front of Australia. Here's an example. This is Alaska. And you see all of these little segments with different names. And those are all bits that have been added together and stacked up to make Alaska. And if you look carefully at what these bits consist of, probably 90% is volcanic arc material. Just like what's happening in the Western Pacific, these bits of volcanic arcs, or a long arc that was slivered into pieces, and now they're various bits. And that makes up most of these pieces. There's also a few pieces of oceanic plateau. This bit in the Wrangell Mountains called Wrangellia, and you find the same thing down here in the Queen Charlotte Islands and Vancouver Island. And those are slivers of oceanic plateaus. And there are also slivers of continental material that just rode up along the western part of North America. So here's Alaska and all of those debris in British Columbia down through California and Baja. And all of this darker gray area consists of pieces that have been added to the front of the continent for the last 100 to 150 million years. This line is the Rocky Mountain front, so that whole mountain belt system sort of goes out to that line pretty much, with a lot of this added on through time. And when we look at the same scale of Australia and all of these pieces, it really has all of the same elements that we find over here, but this is modern and this is complete. It's already happened. So we can grow a significant amount to the edge of the continent, by adding all of these bits of island arcs that form out in the ocean, and some bits of oceanic plateau. And then later, after all that accretion, Western North America is sort of accordioned open. This is the Great Basin in Nevada, and you see all of these ranges really formed by stretching. And that stretching has been accompanied by magmatism, and the amount of magmatism that comes from the mantle will actually add to the mass of the continental crust. Okay, so that's talking about the additions to grow the crust. Now what about subtractions? Well, a big number in subtraction is due to subduction erosion. I'm going to spend a fair amount of time, or slides, maybe not so much time, but slides, talking about that aspect. And I'm going to add at the end something else called lithospheric delamination. And that's something that's just not been taken into account in the addition-subtraction equations that people do. All right, so with subduction accretion, then you accrete a lot of material out to the front, and also you add to it by magmatism. So you grow this arc. With subduction erosion, you actually peel material away. You erode it out from the front, and there are several major differences that you can see very obviously. One is where you have accretion. First of all, you have this big pile of newly accreted sediment out at the front of the wedge, and the older basement rock is very far behind. Number two, this whole area, because you're adding material and stacking it, tends to rise. So over time, that thickening gives you vertical uplift. With subduction erosion, you're not adding material to the front. In fact, you're removing it. So you can often see these basement rocks go right down to the trench, or almost to the trench. And secondly, by eroding away the stuff underneath, you're removing material, and so this forearc area, this region in front of the arc, tends to subside. So if you can get information that tells you about uplift or subsidence, then it can tell you about subduction erosion. Here's a cartoon of the front of the Mariana arc. Here's the Mariana Trench. Very little sediment coming in, and the sediment that is coming in is very old and hard. There's no sediment that gets accreted to the front. Actually, when you dredge front here, you do find signs of accretion, and that is accretion of parts of seamounts that have come in and actually stuck to the front of this forearc. But otherwise, this plate goes under and removes material, and this whole thing will subside. Here are two other examples that have been studied in more detail. This is the Japan margin, so we're looking north in both cases. So the margin off of Japan and the margin off of Peru. And in both cases, you can see down at some depth in the sediments an unconformity, that is a period when that region was up at sea level and was being eroded. And then that unconformity subsided and more sediment was added to it. So knowing the age of the unconformity and the fact that it was at sea level at that time gives you some idea of the rate of subsidence. This says 0.5 kilometer per million years. And the same thing off of Peru, and this gives you a rate of about 320 meters per million years. So in both cases, there is good evidence of subsidence. And in the case of Peru, you can see this crystalline basement going down to within 5 kilometers of the trench axis. Now, Peru's an interesting case because subduction has been going on there since the Triassic, almost 200 million years. And you have nothing to show for it, you know, the few scraps of bits down in the front. And in fact, this crystalline material, a lot of that was formed in, you know, the Andean kind of magmatism and metamorphism that goes on way farther back. So over time, the front has just been eroded back and back, and the arc, the position of the Andes, keeps jumping backwards as well. So one can try to quantify how much material is being removed by knowing how much subsidence has occurred and then estimating how much stuff you have to peel off the front. So this is what the modern situation looks like, and this darker gray was at a time in the past when this unconformity were up at sea level. So it gives you a volume, and if you can date that unconformity, then you have a volume rate of removal. Okay, so there was a recent study by Clift and Vanucci who looked at essentially all the subduction zones around the Earth and try to compare first the accretionary margins with the erosional margins. And the accretionary margins, see Java, Barbados, this pattern indicates the accretionary wedge in front, and this is the crystalline stuff in the back. And notice that the forward slope and that taper between the forward slope and the downgoing plate is pretty narrow, and the amount of material out in front is fairly large. And you compare that with other examples, Peru, Chile, Kermadec, New Hebrides, Ecuador, etc. And you see a fairly steep forward wedge and a steep taper, and in many places nothing or very little material out in front. So there's huge differences between the erosional margins like this and the accretionary margins.
Just where you are on that slide. Can you go
Back one?
Sorry. What is that deduction in Guatemala? It looks like the accretionary margins on the left side.
Well, up here in Guatemala, see, this is a really highly exaggerated scale. In fact, from Guatemala, El Salvador, Nicaragua, that whole stretch has a very thick four-arc basin. That is a basin between the edge of the shelf and the coastline. In fact, in Nicaragua, that basin continues. You know, you can see it on land out in front of the arc. So this is these are sediments that are deposited behind this outer area. And I'm going to show you a section across Nicaragua to give you a better sense what that is. So it's not, so it's accreted in a sense that it's deposited, but it's all coming from the continent. Yeah.
Example, when we were talking about the different materials, you know, just to have an idea, would that material on top of Guatemala, would that be something like limestone, and then, you know, underneath, would it be like a basalt rock or granite or?
You mean over here? Yeah, well, this stuff over here, let's see, the materials out in front are essentially mafic. That is, they're basaltic, and it's very similar materials that you see on the front of Costa Rica and the Nicoya Peninsula and the Osa Peninsula, and that whole band of rocks continues offshore to Guatemala, and it has been drilled out here in the front and up here, so we have some idea of that. The sediment is a whole variety of materials, volcaniclastic debris, There may be some limestone. There are some limestone units in there, but they're not overly thick. So it's a whole array of limestones, volcaniclastics, and other materials. Okay. And so here are, some graphs showing the rate of convergence, the convergence rate in the subduction zone this way, plotted against sediment thickness. In areas that have low sediment thickness and high convergence all tend to be erosional. In areas that have high sediment thickness and low convergence rate all tend to be accretionary. And that's sort of something you might expect. Here's plotting that taper angle or the four-arc slope angle versus sediment thickness. And where you have a high angle and low sediment thickness, it's all erosional. And where you have high sediment thickness and lower angle, it's all accretionary. So they're very clearly separated. This is looking at orthogonal convergence rate versus net crustal growth, sediment thickness versus net crustal growth, and the accretionary margins have the greater computed net crustal growth. And that's just based on accretion versus subduction erosion, etc. So what are the mechanisms for subduction erosion? One mechanism would be having, say, a seamount or some other irregularity on the seafloor subducting, coming down and scraping material off. I'm going to show some examples of that. Another is just the horse and grabens, the faults in the downgoing plate, bringing down water-rich sediments that tend to weaken the base of the upper plate, and when that gets weakened, then it can be torn away and brought down. So these are sort of a couple of mechanisms for subduction erosion. I want to show this one example, and that's in Central America, from Costa Rica up through Nicaragua. And here's a region where you have subduction of one of these large igneous provinces, Cocos Ridge, set of smaller ridges and seamounts that are coming in. And it's a region of subduction erosion. This is just looking at the topography of the seafloor. And you can see the high topography here, the topographic ridges, and much less topographic relief as you get farther up. Looking at that box, here's the base of the trench. Here's the lower plate going down. This is the upper plate over here. And so you can see these seamounts and ridges coming in. And you can see these gouges that are taking place out in the front. And those gouges represent subduction erosion. Here's another view of those gouges, if you can kind of visualize this. This is looking down. This is the Costa Rica part of the upper plate. Here's the trench axis. This is the lower plate. You can see a seamount over here coming in. And in this position, a seamount has just gone under. You can see the bulge and a big slump area here in front. And over here to the south, you can see this bulge farther back and a longer trace coming through. And over here, you notice that there's still a little escarpment and this long trace that can be followed where another seamount had gone through. And if we take a vertical slice, this is looking horizontally at the surface. Now we cut a vertical slice looking at seismic data. Here's the downgoing plate. And right below this area where the seamount should be, that's at a depth of about 10 kilometers below the surface. Just, to me, kind of astonishing that something that deep can still make an effect right at the surface. And you see this track going right along. if you look at a seismic line across that seamount, you can see that over here. It's kind of fuzzy, but the seamount is over here, and the sediment is thicker over there and thinner over here. So where the seamount has gone down, you've actually taken some of the sediment away and moved it on. Here's an overview of this whole area coming down from Nicaragua to through Costa Rica. And one thing that really jumps out is that this edge, this trench edge, is very smooth until you get to this zone where you have lots of ridges and seamounts coming in. And then it takes a step in, and you have, you know, all of these bites being taken out, and this sort of whole area has stepped in about 10 kilometers. So you've removed that much of the front just because of those seamounts. So it's pretty obvious that you're removing material here. So I want to jump over to here, and this is this part north of where the seamounts are coming in. And we've done a fair amount of study there. That is kind of a sketch overview of what the margin looks like. Comes down to the trench. And here's a seismic line that shows basement rocks coming down to within, that's 1 kilometer, so it's about 3 or 4 kilometers from the trench. And there's this little wedge of material here. And these are sites that we drilled out here in front of the trench, and then these two in here. I'll first focus on that. And if you look at this line, this is measured in depth. So you look at this line here, or well there, and this well here. We have very good control of the ages throughout each of these wells. You notice this is thicker than that. And I'm going to just show these two, the next slide. And that's the distribution of age versus depth. So age is this way, depth is that way. And you can see that that sedimentation is very rapid up until about 150 meters. Then it's slow out to about this point, about 200 meters, and then rapid down to the about 400 meters. And that goes up to zero age. That's before the trench. When you get up on the slope and drill down, you see the same thing. The deeper area is fast sedimentation. This intermediate zone is slow, and then very rapid sedimentation up to zero age. So we come to zero age. But that's maybe zero age, but it isn't zero depth, because it's 370 meters below the seafloor. So all of this stuff from here is being subducted with virtually nothing left behind the other side. So we know that things are at least being subducted. And now coming back to this line, we've got a well right here. No, we don't. I can't see it, but I think it's somewhere right about here. So there's one that goes through most of this sediment apron up here, and then one right next to it at somewhat greater, little greater depth that goes down through this, this hard layer. And what we found was that the one that went through the hard layer is now down almost at 4 kilometers, but the rocks were formed right at sea level. They're a very distinctive kind of carbonate breccia that shows structures and veins that had to be formed at sea level, and they're about 16 or 16.5 million years. So that means these rocks 16 million years ago were up almost at sea level. And then the other site went back to about 8 million years, and this is the depth of the well right now at the surface. But as you go down, as you get to older ages, the depths of the foraminifera, the sediment, indicate they get shallower and shallower. till about 6 or 6.5 million years ago. And then from about 6 to 16 million years, doesn't seem to be much change. So from about 6 million years to the present, there seems to be a rapid subsidence. And that indicates subduction erosion. So here's the present margin, the present shoreline. There's down near the trench. But 6.5 million years ago, that was shoreline. So if we make that shoreline 6.5 million years ago, then we have to add a margin out in front of that. And that indicates about 50 kilometers of material has been removed in a fairly short length of time. Just show this profile off of Nicaragua up here. And I'll first show a time section. So the vertical axis is in time. It shows a lot of detail, but it does distort the geometry. So you see this fairly thick sedimentary basin that you were asking about out in here. And then out in front, this real strong reflection that is really basement. It's that same kind of basement that you find in the Nicoya Peninsula. And this is in depth, so it gives you a true geometric image. So here's the downgoing plate coming down here. We can see that really well. And that very strong reflection. And on an adjacent line, that reflection actually comes to the surface, and we dredged it to find the same material we find in Nicoya. Okay. This, yeah, let me, I'll talk about this. This is a refraction line that was done in that same region of Nicaragua. And what it's showing is the downgoing plate. This dark, the really black color is velocities equal to mantle velocities. And the lighter colors, the lighter you get, the lower the velocity, the seismic velocity. So it indicates that this area out in front, the coastline's here, so there's an area out in front of this big basin that is really a different feature. And that is the basement of Nicoya type material. And if that same amount of subduction erosion has occurred in 6 million years, then this is the present section with this little plateau and this big basin. And 6 million years ago, it was much wider. So all of this would have been eroded away to give you this by subduction erosion. Okay, so getting back to the global picture, most of the subduction zones, almost 60% of subduction zones, are erosional. So on that basis, you might think that, that the continent should be disappearing pretty rapidly. The problem with making continents and island arcs disappear rapidly is that throughout much of geologic time, certainly the last 500 million years, what's known as continental freeboard, that is the position of the continents relative to sea level, hasn't changed much. I mean, sea levels have gone up and down for various reasons. Having ice, you get lower sea level. When it gets really warm and no ice, the waters get less dense, and they rise somewhat. So you get flooding. But that just oscillates over time. And so we're not losing a lot of continental mass, and we're not losing a lot of these island arcs go back, certainly through the tertiary, 50, 60 million years, and we're not losing a lot of island arcs. I mean, there's some places like South America seem to be losing a lot from the front. Of course, you're gaining it back in the Andes. And so that appears to require a significant amount of magmatic activity, which, except in a few places, is hard to quantify, in order to keep this balance. And so to try to maintain the balance, this is what Clift and Vanucci feel is the overall balance at all of these different subduction zones, where everything below the line is a net removal. So places like Ecuador, Colombia, Peru, northern Chile, the Philippines, and over here in Kamchatka seem to be negative. They're losing material. And virtually all the others, places like Costa Rica, the Ryukyus, etc., are practically zero. But all the others seem to have a positive increase, so that on the whole, we may be adding more material than we're losing. And looked at in a pie diagram, this is material added to the crust magmatically. This is added by accretion, fairly small. This is lost to the crust by subduction erosion, and this is sediment that's lost by subduction erosion. So on the whole, it's fairly balanced with the plus side being slightly greater than the minus side, and mainly in order to keep that freeboard balanced with a number that is very hard to constrain, the actual amount of magmatic material that's being added to the crust. Now here's one other ringer in this whole thing that may or may not be really important, and that is a process called lithospheric delamination. This is the Mediterranean area, and it's from a recent Nature paper showing some data, but just focus on the cartoons here. And that's showing crust, lithosphere, and the asthenosphere. Well, this crust lithosphere, this is mantle lithosphere and crust lithosphere. Here we have Africa colliding with Europe, giving a thickening lithosphere. And over here, we find that thickened mantle lithosphere pulling away and being removed. Now that process is actually one that is fairly well documented. This is in the Carpathians, and it's a section, but it's showing, here's the mountains up here, and this green would be the mantle part of the lithosphere that pulls away in a slab that's still seismically active. So you can actually see this vertical zone of seismicity below the mountains. And then you have a fairly high amount of heat, which would give you uplift of this area here and a higher heat flow developing. And this kind of process has been suggested in a number of places. Now, does that have any effect on the change in the continental crust material? Because this is really pulling away the mantle part of the lithosphere. So in a cartoon like this, it doesn't necessarily affect the crust. Here's one more example, and that's the Sierras. The Sierras, here's the high part of the Sierras, Sierra Nevadas, and if you've taken basic geology, you know that the fundamental basis of mountains is that they have roots, right? The mountains stand high and there's a low density root holding it up. Well, you've all been to the Sierras don't have a root. There's nothing holding it up. Well, it's not true. What's holding it up is the low density of extra hot upper mantle. And it's extra hot because the mantle part of the lithosphere has sort of dripped away. So here's a cartoon of the mantle lithosphere kind of dripping away and giving you kind of a higher velocity zone underneath the foothills in the Great Basin, and a really hot low velocity zone under the Sierras. That effect, here's another paper with a different cartoon, that effect may be responsible for the magmatism that one sees in the eastern part of the Sierras, Owens Valley, Long Valley, Mammoth Mountain, monocraters, etc. Okay, so does that have anything to do with crustal material? Well, there's also a recent paper that tries to make the case that materials in the lower crust can have low enough quartz content that if you bring them down to about 50 kilometers, they become negatively buoyant and can just sink down into the mantle. And if that's the case, then it may be possible that in areas where you have lithospheric delamination, if they entrain parts of the lower crust, that you could actually be removing lower crustal material down into the mantle. It's not a way of adding lithospheric material, except in the last slide, except if you form melting down in the mantle and you add that melted material to the crust. So that would be a process of adding mantle material to the crust, and this would be a process of removing it. We know so little about this process that there's no way we can quantify it, and none of the studies do. So that's sort of where we are, or where I am, in understanding, of this mass balance. Are continents growing with time, shrinking, about the same? There are definitely places where we can see the front of the continents just being chewed away like crazy. Magmatism may be keeping pace or more than keeping pace with that process. For most of the numbers that I've indicated, I went by really quickly, don't really have direct control on. It's saying, okay, we've got control of a few places. This place looks something like that. We'll give that the same kind of number. But we don't really know in a lot of places what that is. So it's a fairly simple question with a very difficult answer. Yeah. So, any questions? Thanks.
Can I ask?
Yeah.
So you indicated in the previous slide, especially the convection that was happening in conjunction with the delamination.
Like that?
Convection driven by the fact that there's this big thing getting in the way.
Yeah.
Is it a chicken and the egg situation? What comes first? Is it convection that's driving the delamination, or is it delamination that's causing it?
Well, I would think in this case, once you start delamination, you got to put it somewhere, right? You got to make room for that slab, so that has to, a asthenosphere has to flow out of the way. And since it has a fairly low viscosity, because there's partial melt, it can flow pretty readily. Yeah. But how it starts is a good question. Why did it initiate in the first place? I don't think anyone knows. Yeah. Yeah.
It's just a whale of a surprise that there's so much data input. Drilling off of Nicaragua.
Off Costa Rica and Peru, Japan, Guatemala. Yeah.
Word.
Yeah.
So how large is the team that's working on that?
Well, it's not exactly, I mean, there are people working on these things, from all over. So
It's whoever jumps in and helps out.
yeah, I mean, it depends on what question you're asking. You mean on some of the drilling data or the whole problem, or?
The team that's drilling down there in Central America.
Yeah, I was the co-chief scientist on the first drilling leg, where we discovered all the subsidence. And yeah, there's about 25 5 or 6 people as part of that program. But you know, there's drilling that continues in various other places. Yeah.
How much cooperation do you get with the oil people?
Well, none for drilling. And in fact, it's an interesting question. You may be aware that we're facing some budget problems. And so we have 2 drill ships. The US has a drill ship and the Japanese have a drill ship. And because of the price of oil skyrocketing, we can only keep those ships running 6 months of the year. But we've got to fund them for the whole year. Otherwise, just sitting in the dock takes a huge amount. So you don't even have your full half year. You've got to pay for the stuff. So we're trying to interest oil companies in using the ship in those other 6 months. You know, but as far as funding the science, that hasn't been anything from oil companies.
Do the oil companies report back what they're finding at different depths?
Oil companies tend not to, and it depends on the you know, the national regulations. The U.S. companies can keep their data secret forever. In Australia, Papua New Guinea, I think there's a 3-year limit. All the data has to be made public. So, so when you're working in that part of the world, it's great because you do have access to all the data that they take in.
But are the oil drills going that deep? I mean, in terms of what you're interested in?
Yes. Of course, they tend to work in different environments. They have no interest in subduction erosion, and some of the things we're talking about is getting to the seismogenic zone. There's no interest there. But there are really key scientific problems that can be helped by oil. And in fact, there was a recent drilling leg that happened in the Gulf of Mexico with a lot of industry data input. It was funded by the National Science Foundation and the other groups, but the oil industry contributed a huge amount of data.
Have you entered into any kind of collaboration with any European entity about this? For example, I'm just thinking of the Mount Etna in Italy and, you know, how much activity is happening there. And I just didn't see, I saw your Iberian and North Africa
Right.
slides.
Right.
Are you collaborating with them?
Yeah, I mean, the drilling program is truly international. All of our work in Central America has been done collaboration. Certainly the Germans have a big Central America program as well, and so we've done a lot with them, as well as Costa Ricans and Nicaraguans. Now in Spain there's a lot of interest. I mean, and you're right that you know, Mount Etna, there's a lot of activity. I haven't personally worked there in Mount Etna. You know, I'd love to, but there's only so much I can do. So yeah, the answer is yes. And on every drilling leg, it does consist of many different nationalities. Yeah.
Eli, early on you were showing Papua New Guinea, the Ontong Java Plateau.
Right.
Is it the feeling that the boats of Northern Australia will be preserved by the collision between Papua New Guinea and that most of that would just be tacked on? Showed the example of the California and
Right.
Washington.
Yeah, I think the thick bits will be preserved. It's there's a real question about what happens to these oceanic plateaus like Ontong Java. We definitely see pieces of them, but you know, when you look at the pieces of Rangelia, you know, you add that up and it's a pretty small amount of stuff, and you know, that probably was part of a much larger plateau. Now the interesting thing is, if you take a basalt and you get it down to about 50 or 60 kilometers depth, and you get it hot enough, it will change to eclogite, which is denser than the surrounding peridotite. So then that can just keep on going. So you can get a plateau deep enough, then it drags the plate with it. Yeah, with Ontong Java, there are little pieces that you can see in the Solomons, you know, but we don't see big pieces of Ontong Java. Island arcs, you know, will accrete. You know, they're thick enough and they'll accrete onto the front. There are small ocean basins like the Solomon Sea, and that'll clearly completely disappear. Yeah.
You were just talking about how the salt may become denser and variable farther down. I've heard of the hypothesis that there may be like some oceanic slabs, subducted slabs, like a graveyard. Is there any seismic evidence for it?
Yeah, I mean, there are all kinds of, there's a whole history of graveyard hypotheses, and there, you know, it really has been resurrected in a sense. There's an early one that thought that since you could only see earthquakes down to about 650 kilometers, that what happened is the slabs went down to the core mantle boundary and then just kept filling up the mantle, and over geologic time they kind of reached that level, you know, with old graves. That's not true because we can see slabs in some places going down very deep. There are new ideas looking at much more detailed seismic images from earthquakes that do suggest that some of these slabs can get down as deep as the core mantle boundary. In fact, I had a bunch of stuff on here. South America, I don't know if I have any. These are some slides from seismic tomography, and you can see that the blue areas are high velocity, the red areas are low velocity, and so the blue is really following these slabs. And for the most part, they, you know, they do sort of, you know, they kind of shallow out in these shallow depths. Here's one that's going through, and yeah, so here's over in the Indonesian area. Well, they're not going to, they're going down at least into the, deeper into the mantle. Below that. I thought I had one that went all the way through. You know. Any of these? I don't think so. So with these, at least they, there is indication that these slabs can go, you know, halfway through the mantle, if not deeper. So yeah, there are those ideas, and I don't see anything wrong with them, you know, because we do see evidence of the slabs going deep. But at least the earlier graveyard, that the whole mantle was filling up with slabs, that isn't right. Because they, you know, once it's down in the mantle for some time, it just becomes part of the deeper mantle.
Questions?
Good.
Thank you. Eli very much for his talk today.
Thank you.